Many of you know John. He's a professor in computer science at Rice University, primarily doing most of his work over the last decade, I think, on performance tools and tools development for making programmers more efficient in what they're doing. So, John, it's all yours.
Okay. Thank you, Jan. So I hope I'm not going to repeat things as I get started here, because unfortunately I missed Steve's talk. I was giving my class across campus. We were hoping to stream his talk, but it didn't happen. So today I'm going to talk about the work that my group has been doing on performance tools for GPU accelerated computing. So to give you a little bit of context for this work, this is principally funded through the DOE Exascale Computing Project, which is part of the National Strategic Computing Initiative. So this is a partnership between the DOE Office of Science and the National Nuclear Security Administration, the NNSA. And the goal is to develop a new class of HPC systems that can deliver exaflops, 10 to the 18 floating point operations per second. So the scope of the Exascale Computing Project is focused on hardware and technologies and architectures, applications, and system software. And so my work falls mostly in the area of system software and tools, but I'll just give you a very brief preview of what else is going on. So in the architecture front, today we've moved to GPU accelerated systems. So for the reasons that Brad McCready said in his talk yesterday, that GPUs are very good at performing computation very fast with a high efficiency per watt. And so the Summit supercomputer has 2 IBM Power processors per node and 6 NVIDIA GPUs. Something to note is that the GPUs are responsible for about 47 teraflops of performance on a node, and the CPUs are only responsible for about a teraflop. And so the bulk of the compute capability is on the GPUs. And so that situation is going to continue with the next generation systems. So the forthcoming exascale platforms for open science at Argonne National Labs is a system called Aurora, which is going to have, it's planned to deliver at least an exaflop. And so each of the nodes on it has 2 Xeon Sapphire Rapids processors and 6 Ponte Vecchio GPUs. I'd love to know a little bit more about them. Despite having signed innumerable NDAs, I don't know very much, despite the fact that I'm inside the project and I'm developing software for them. But that's neither here nor there. So the second system is the Frontier system that's going to be at Oak Ridge National Labs, and so that's also going to be delivered in the 2021 timeframe, optimistically. And so the Frontier system has a single next-generation AMD EPYC CPU and 4 of the custom-built Radeon Instinct GPUs surrounding it. And so on both of these systems, of course, the lion's share of the compute capability is on the GPUs. And so we're very interested in how to support GPU accelerated computing. So the Exascale Computing Project is working on applications in a variety of areas, and so I don't have time to discuss these in detail, but there's applications in national security related to stockpile stewardship and energy security, economic security, scientific discovery, earth systems, healthcare, you name it. So there's a large portfolio of applications, and if you go to exascaleproject.org, you can find out more details about what people are working on. So my work is mostly in the system software area, and so in the ECP, the system software area includes work on programming models, development tools, math libraries, data and visualization, as well as a software ecosystem for delivering these whole things as a package. And so my focus has been principally in the interaction between the programming models and the development tools. And so I'll say a little bit about how people are expecting to write these applications for exascale systems, and then what that means for the tools that we're working on. So in terms of the action on these systems, there's a lot of compute capability on every node. And so it's really important to use the nodes effectively. And the programming models that are being employed for these systems are not so different than what people have been using for a while. So OpenMP has been evolving since about 2000 or so, and there's been a big focus on adapting it to GPU accelerated systems supporting attached accelerators. And then there's also been some work at the national laboratories on these Raja and Cocos template-based programming models that use C++ templates. And I'll say a little bit about each of these. So the OpenMP5 model, you can offload computation onto accelerators, and you do this principally through just adding some directives to your program. And so you can tell it that I want to map data onto an accelerator. And so the target data construct on the outside says, for the duration of this while loop, we're going to map this array into the accelerator, and we're going to allocate a new array, a new. And then the loops inside this while loop are annotated with directives that say, I want to spawn a team of threads on the SMs in the GPU, distribute the iterations to these teams, and then share them among the warps that are a group of threads that are performing the computing. And so this OpenMP model is basically take your generic code, maybe it was a single threaded code, and the idea is with a little bit of light annotation to your program, then hopefully you can get this to run well on a GPU. Now, whether this is actually a performance portable model, that's a separate matter. Notice that, well, I guess it's not shown here, but sometimes these things are marked up with like the number of threads you want it to run on, and that can be sort of specific to the particular architecture you're targeting. So that's OpenMP5. And so this is considered kind of one of the flagship portable performance programming models that the DOE has been backing. At Lawrence Livermore National Lab, they're working on something called a Raja portability layer. And so the idea here is on the left, it shows a loop written in C, and then on the right is a loop written in Raja. And so principally, you've replaced the for with a Raja for all, along with some executor policy. And the key thing is that the internals of the loop body are the same. And the idea here is that they're introducing a layer of abstraction, and that this Raja for all underneath, it could be implemented by OpenMP directives inside the C++ templates, or it could be implemented directly by CUDA or AMD's HIP. And what it does is it provides a layer of abstraction so that the application developers only have to rewrite their code maybe once. And then if today we're programming using CUDA on a particular machine, and then 5 years from now, when this next generation of machines are gone and they're replaced by something else, the goal is that the application developers don't have to rewrite their code again. Instead, the people who built the templates would have to change the internals of the templates, and then the whole application would just map onto a new architecture. So at Sandia, they're working on another template-based programming model, and this one is a little bit different. It has abstractions for the data structures as well as parallel execution. So it has these execution patterns like the reduce pattern that's shown here, where it says Cocos parallel reduce. And then it's applying the same idea. It's using a C++ lambda expression that represents like a singleton loop body for a singleton element that you're working on. The difference with Cocos, though, is it kind of takes over the data allocation. And so using Cocos, you express your data as Cocos arrays, and then it's abstract. It's up to the implementers of the array abstractions as to whether it's row major or column major or tiled or strided or whatnot. And so this is another C++ abstract programming model. And again, then they can layer this on top of CUDA or layered on top of OpenMP, the underlying implementation layer. So for us, we have to be conscious of the fact that people are developing these applications using these different programming models. And so OpenMP is going to be fundamentally transformed by the compiler based on these directives. In the template-based programming models, the compiler is also going to perform the transformation, but the template is providing sort of direct recipes for exactly how to do that. So when you're running programs that are written using these models on these GPU-accelerated computers, there's a lot of things that are important. And so to use the whole system effectively, well, the main thing is we're worried about the compute performance of these GPU-accelerated compute nodes. We have to use the GPUs effectively. Second thing is we're interested in the data movement costs both within and between the CPU and GPU memory spaces. There's also costs of internode communication, the messaging typically using MPI between the compute nodes, and the I/O as well for these large-scale problems. So for running large-scale applications on these machines, there's many different ways that you can destroy the performance of your code. If you have insufficient parallelism, or you have load imbalance, or you have some sort of serialization or replicated work, or just lots of parallel overhead where you're exploiting parallelism at too fine a grain, all of these things can cause you to lose massive amounts of performance. And so what we would like to be able to do is understand what these kinds of performance losses are and whether they're due to the way that you're computing or communicating or your imbalance of work. We'd like to be able to identify all of them. And so for us, one of the things that's both a complication and a concern is that you've got these multiple compute engines, you've got the CPUs and we've got the GPUs, and they've got vastly different characteristics and vastly different capabilities and concerns as to what's important. And so the GPUs, of course, are the most important because that's where the most of the compute capability is. So there's multiple memory spaces. The CPU and GPU have their own memory spaces, and they have their own memory hierarchies that are different, and we have to worry about the data movement between them. And then the other thing that's complicating is that the computation is being executed asynchronously. It's going to be launched on the GPUs asynchronously. In terms of the applications, these are quite complex, and so for Livermore, they have this code called Mercury, which is a Monte Carlo radiation transport code. And according to Dave Richards, who's one of the application developers there who's involved in the ECP project, they're dispatching GPU kernels that invoke 100,000 lines of code. So they're saying like for all particles, and then here's 100,000 lines of code to execute as like part of the GPU kernel. And so if you have a tool that just says, boy, that's slow, that's not really going to help. You need to know, like, what am I going to do in my 100,000 lines of code in order to fix the problem? And so that's the problem that we've been trying to tackle. So in terms of the challenges for tools, we've got these diverse programming models, the OpenMP, the template-based programming models. We've got extreme scale parallelism on the nodes. And so if our tools sort of serialize internally, then we're going to disrupt the parallel performance of your application, and any measurements we take are going to be worthless. There's different ways to measure. So on the CPU, we're typically measuring the activity using sampling. On the GPUs, we're using a vendor-supplied library. So NVIDIA has a CUPTI library, the CUDA Performance Tools interface. AMD has something called the Rock Tracer library for tracing their ROCm GPU infrastructure. And so with these software layers, we get callbacks when operations are launched on the GPU, whether it's launching computation or launching memory copies. We get a callback that says, this is what's about to happen. And then there's a stream of events that are coming off the GPU saying that kernel you launched, well, it started at time t and it finished at time t prime. And so, and then in order to get detailed performance information, we can only measure what the hardware can monitor. And so one of the things that's a strength of the NVIDIA GPUs is that they have this ability to do PC sampling. So you can actually, the GPU hardware will sample at the instruction level and will attribute costs to say, this instruction isn't making forward progress because it's waiting for memory. This instruction isn't making forward progress because it's waiting for a special function unit, like it's waiting for a divider. And so that can be very helpful for trying to understand these applications in detail. And then finally, there's so many things being launched on the GPU so frequently, and we're getting these callbacks. We have to have a low overhead measurement infrastructure in our tool. Otherwise, the tool is going to slow down the application. So the set of tools that we've been building are called HPC Toolkit. There's a bunch of different HPC toolkits. IBM has an HPC toolkit. Intel has an HPC toolkit. Both of theirs have spaces in it. We say those are the HPC toolkits with an air gap. So ours is the original, and if you search for it on the web, you'll find us. So the way that you use this is you compile and link your programs the way that you normally do. There's no required changes to your build process. If you want to have the performance map back to individual source lines, then you need to add a -G to your make files, or for GPUs, in the NVIDIA GPUs, you add a -line info to make sure that the GPU is generating line maps so that you can get the performance reported at the individual source lines instead of just at the level of functions. We don't need this information, but if you want detailed performance reports, then you can add these options along with your optimization flags. So then the second thing we do is we launch you would launch your application using our script HPC run. And so this is something where if you're running a sequential code, you say HPC run your application. If you're running an MPI code, then you might say MPI run or S run, HPC run your application. And what it does is it preloads the code for the performance tool into your application's address space. And that code module that we add to your address space is going to track as all of the other code gets dynamically loaded into the address space and as threads get created and processes fork and things like that. And so it's going to kind of keep control of the threads and processes to know what's going on inside the application. And then it's going to measure something called a call path profile. So when we're sampling on the CPU, you'll get interrupted by either a timer or a hardware counter. So it might be a cycle timer or say every millionth cache miss interrupt me, and we'll see that I'm at a particular location, and then we will unwind the call stack to find out where we are in the call chain. So it's like main calls solve, calls matrix vector multiply. Okay. So in the support for the GPUs, what we're doing is we're unwinding the call stack to find out where the GPU operation is invoked. This is particularly important for these template-based programming models or these OpenMP-based programming models because the code that's running there isn't something that you've written, okay? You instantiated this template, and then 15 layers down the instantiation, something got sent to the GPU, and it's got a 2,000-character name. And the only way you know what it is kind of from the source line in the code where the template got instantiated. You know what you were trying to do at that point. So we unwind the call stack, we generate a unique tag. The tag gets propagated into the GPU so that when the GPU reports the performance measurement data, it's all associated with the tag so that we can associate the measurements back with the calling context and where the operation was launched. So one of the neat technical things inside our tools is that we've built something called weight-free data structures so that we're using this for communicating between the application thread that is collecting these tags and the GPU monitoring thread, which is collecting the streaming information off the GPU so that they can coordinate and attribute the cost back to their context. And the weight-free data structure guarantees that the application threads don't wait for the GPU monitoring thread, and the GPU monitoring thread doesn't wait for the application thread. And this is important for not disturbing the running time of the application. So we're collecting information about kernel execution times, about data movement, the times and the number of bytes moved. And we're also using PC samples to get detailed measurements at the instruction level. And we're correlating all that back to the source code with where the kernels were launched. And then finally, we're also producing these activity traces like some of the other tools do. So NVIDIA's tools will also produce these trace lines. So then in order to interpret this information that we're measuring, when we're measuring the application, we're measuring things at the level of individual machine instructions, and we have call chains that are represented by instruction addresses. And so we have a binary analyzer that you use to analyze your application, to analyze the machine code, the line map, whatever debugging information about inlining that the compiler recorded. And from the analysis of the machine code, we extract loop nests. We build something called control flow graphs to understand the branching control flow in your application. The reason why we do that is to identify loop nests in the application because loops are often where the action is. And we want to be able to map all of those transform loops back to the source code. So for the GPU accelerated systems, we've built this capability for this fine-grained analysis of the NVIDIA CUDA binaries. So the only reason why we've done this only for NVIDIA so far is because none of the other GPUs have this capability of being able to measure at the machine instruction level. And so if we're measuring at the machine instruction level, we want to be able to interpret the machine instructions and tag things back to the source code where it came from. So inside our binary analyzer for these CUDA binaries, we're relocating these functions which all begin at address 0 by NVIDIA's convention. We ingest the line maps. We use NVIDIA's NVDisASM tool to compute control flow graphs. NVIDIA won't provide us an API to allow us to manipulate the machine code directly, so we're using their tools to grab control flow graphs. Then we ingest that information into our own tools. We identify loop nests, and we correlate this with the inline code and build this program structure for the CUDA binaries. It includes functions and static call sites and inline functions and loops. So then finally, we take the measurement data from multiple threads, multiple processes, multiple executions, GPU streams, and we combine this all together and synthesize some presentations of the program performance. So what we're doing for the GPU functions in this analysis phase is we're analyzing the GPU machine code to identify function calls. We construct a static call graph to figure out who calls who. We identify functions that have multiple calls. And then when we're measuring using NVIDIA's PC sampling, the PC sampling says, I saw so many samples in function f. And now if we see that f is called from function c, then we know that all of the costs that were incurred by f were incurred by this call from c. If there's multiple calls to f, then in fact we actually use the measurement data from the PC samples to say, well, if there's twice as many call instructions that were sampled for this call to f than this other call, then we're going to give twice as much cost to this call site as to that call site. So it gives us a way of apportioning the costs within the GPU. And I'll show you how this works out. So this is actually an important thing in order to understand these complex applications, and this is something that no other tool does. So then finally, we have these presentation tools that enable you to explore the performance data from multiple perspectives. So you can see sort of profile-oriented views that are correlated with the source code. You can see time-oriented views, trace-oriented views that let you see the behavior evolve over time. So inside the code-centric user interface, we present information about the GPU operation statistics like invocation counts of the various functions, the number of bytes of data moved, the amount of time spent in each of the operations. We have kernel-centric metrics like how many registers they use, how many threads they used, how many threads per block, memory usage statistics for whether they're using static, dynamic, or shared memory. So this is like similar to what NVIDIA's tools are presenting. We have instruction stall metrics. NVIDIA's Insight Compute will also present this sort of thing. And so one of the key differences between what we are doing and what NVIDIA is doing is sort of highlighted here. So I mentioned that we were doing this approximation of GPU calling context trees. So I also mentioned this code called Mercury from Lawrence Livermore that has 100,000 lines inside the kernel. And so what we're working with here is a code called Quicksilver, which is a proxy app for Mercury. It's a GPU-accelerated Monte Carlo radiation transport code. And so what we get with the flat PC samples is we see that there's a call to this cycle tracking kernel, and then there's a whole bunch of functions that got invoked on the GPU. So this is after optimization, and after all of the inlining, these are the functions that are left. And so this doesn't have 100,000 lines of code. It's got several thousand lines of code, and it's broken up into functions, and not all the functions were inline. That's the main point here. And so all we know is when you launch this kernel, all these other functions got executed. And we don't really have any organization. We just know that costs were incurred here. So then what our tool does, so this is without doing this reconstruction of the GPU calling context. So what our tool does instead is we're reconstructing these approximate GPU calling contexts and apportioning the cost of the GPU functions. And so here you can see that cycle tracking kernel calls cycle tracking guts, calls collision event, and it's got some inline code and some loops inside it, calls macroscopic cross-section. And so this is a view of the code that is much more similar to how the application developer would view it. They would say, well, the cycle tracking abstraction works in the following way. It calls cycle tracking guts, and cycle tracking guts is working at the level of collision events. And so what you're seeing here is a heterogeneous call stack that up at the top, it starts on the CPU, and then it gets to the middle where we have the red box around it, and then all of the rest of that call stack is details that we've reconstructed on the GPU. And then we have the measurements from instruction-based sampling over here that show you how many machine instructions and how many stalls were incurred in each of these contexts. So I mentioned earlier that there's this array of programming models that are being used on the GPUs. So one of them is the OpenMP using the target for offloading. And so this is showing one of these source code oriented views of a code called QMCPAC. It's another quantum Monte Carlo code. And so they're using the OpenMP programming model and then offloading, using the OpenMP target to offload code on the GPU. And so what's shown here in the magenta is the code that's being offloaded onto the GPU. The Raja and Cocos template-based programming models, we get to see in the calling context reconstruction that starts on the CPU, we get to see the instantiation of multiple levels of these inline templates, along with the template-generated code that is occurring on, that is running on the GPU that says Cocos parallel launch constant memory, and then is performing some operations. So regardless of the programming model, we're able to attribute these costs in context, and we now have a tool that's giving us a very similar view to what we were used to seeing with profiling on CPU codes. And so finally, using this fine-grained performance analysis and this loop level analysis, we can see detailed GPU performance metrics attributed at the loop level. And so if you've got complex data movement going on, like you've got transposes and whatnot, you can see how the transposes are working, and you can see their memory hierarchy usage at the level of the individual loops. And so that can help you tune the abstractions and decide whether you've got the memory allocated right, whether some of it should be in shared memory or constant memory or texture memory, or whether it all should be in global memory. And finally, we have these trace-oriented views, and so this is showing a view from a code called NIX that's being developed at Lawrence Berkeley National Labs. And so the lines here that are shown in kind of a plum color, those represent the MPI ranks. And so what we're seeing here is that each of the colors actually represents a particular procedure. And so depending upon the call stack depth I show, it's going to reveal the code at different levels of abstraction. So at the top level, you might see that the MPI process is running main, and then if you look down a little further, then you'll see that it's doing initialization and then solve, and if you look down further, then you'll see the detail inside it. And so at this level of abstraction, we have the MPI processes are shown with the solid lines, and then the GPU trace lines are shown using these flecks. And so the interesting thing here is, in fact, there's no overlap between the computation on the different GPU streams. And this came about because they were using a callback interface that was signaling that the GPU computation was done and then deallocating the data. And by using that callback-oriented interface, in fact, it destroyed the CPU-GPU overlap. It destroyed the GPU stream overlap, and that was something that was a bug in CUDA. And so the application developers were surprised by this behavior when they see this view. So in terms of ongoing work, we're working on designing a measurement API for the Intel GPUs as soon as we know something about them. We're working on a deeper integration with the AMD GPU monitoring framework. We've been working closely with the group working on Rock Tracer and getting some changes made to support our things. We're working on support for analysis of machine learning frameworks. There's PyTorch, and I don't know how TensorFlow got spelled that way. I guess I leaned on the keyboard when producing the slides. But it turns out that these frameworks they have huge binaries that are gigabytes. And so doing the binary analysis actually is a chore, and we do this actually in parallel in order to accelerate it. We're working on improving the scalability of our tool. It used to be that when we're collecting just a few metrics for the CPU, that using a dense representation was fine, but now if we have like hundreds of metrics for the GPU, we don't want to have hundreds of metrics for everywhere in our calling context tree. My student Karen Zhao, who's one of the K2I fellows supported by Exxon, he's working on a GPU performance advisor that's doing analysis of the machine instructions and roofline analysis of the GPU code. And finally, we're working on some analysis of these timeline views to get a better understanding of the GPU utilization over time.
Thank our speaker. He left room for one question. You have a question here?
Yes.
Hold on.
Hi, thank you. Very interesting talk. So you mentioned template-based programming models for parallel computation. Do you have anything to comment on the C++ 17 standard that also offers parallel execution policy?
Do I have any
Anything
comments
to
about
comment? Does your framework support it in any way?
Does our framework support the C++ standard?
17, yes.
The C++ 17. So basically, if your compiler supports it, we're agnostic. If you compile into machine code, then the tool will work with it. There's nothing special about C++ 17 as far as we're concerned. We deal with the applications at the level of machine code. So if your compiler generates it, then it'll be fine.
I'm going to take the liberty of asking you one more question. So you know where your bottleneck is by using your tool. Do you get any advice to the developer how they can actually improve their code?
So one of the future work pieces is the GPU Performance Advisor, okay? And so like right now, the tool presents, we go to a lot of work to collect this measurement data. And when you take these measurements and you put them in the hands of my graduate student, he says, I know immediately what to do. And he says, oh, I'm going to reallocate the memory so that some of it's in shared memory and we're not putting so much pressure on global memory. But right now, interpreting all of these detailed statistics is a bit of a chore. And so that is the active area of research.
Okay. Let's join me in thanking John again.